Thank you for coming tonight. So I wanted to tell you about, or ask the question, can physics stop climate change? So let me begin by the basic facts, which we all know, that the carbon dioxide concentration in the atmosphere has been growing steadily. It's been measured carefully since 1958 in Hawaii. This is the famous Keeling curve. And actually, this is not quite up to date because now we've exceeded 430 parts per million. We see this oscillatory red signal here. That's the seasonal cycle. During the springtime in the northern hemisphere, plants absorb carbon dioxide. Then in the fall, they die, they release it. And since most plants are in the northern hemisphere, we get this kind of oscillation. And that is our first hint. There might be some approaches to removing carbon dioxide from the atmosphere, which is something I'm going to turn to near the end of the talk. Now, this is a record of recent temperature. This is from July to June, so this is the course of a year, and these are different decades. So this is back in the 40s, 50s, and as we progress forward to the present time, we see that in 2023, there was this sudden jump in temperature. The temperature was certainly increasing around the Earth, but there was this dramatic jump that has occurred. We don't fully understand what's going on here, but we do understand this overall trend, and I want to begin by explaining some of the physics behind that. This is another plot showing the growing temperature of the Earth from 1990 to 2025. This is the latitude, so this is the North Pole, this is the South Pole. And you can see that there is this accelerated warming in the high northern latitudes up in the Arctic. This is a successful prediction of climate scientists. Climate scientists, in fact, Nabi, who won the Nobel Prize a few years ago, made this prediction in 1975. Over here on the time chart, before any evidence for it occurred, and now we see it as a dramatic warming of the Arctic. One of the consequences of that warming is that there are now very large fires burning in the boreal forests of Canada. You can see from this picture from space a few weeks ago, smoke from the fire heading up to the North Pole. And then there, of course, is the terrible tragedy that has occurred just a few days ago in Texas, the flood that has killed many people. Very likely it is something that was worsened by climate change, putting more moisture into the atmosphere and making that event worse than it would have been otherwise. But before I get into the physics, I want to acknowledge the Aspen Center for Physics, because it was here in 2006, or 2005, I guess, we had our first workshop that brought together physicists from across a wide diversity of fields to think about climate change. So we had a workshop called Novel Approaches to Climate, and this was the very first workshop in the United States that sought to overcome the siloing of different fields of physics. And this is the first page from our proposal. And this has led to a mushrooming of activity across the United States and, in fact, across the world. The Kavli Institute for Theoretical Physics has had many climate physics workshops. One is going on right now. I just came from it, focused on Arctic climate change. There have been other workshops here at Aspen. The Max Planck Institute in Dresden has had climate physics workshops, and the American Physical Society, which, as Clara mentioned, I'll be president of next year, has a very active group on the physics of climate with top climate scientists like Michael Mann and Tiffany Shaw. So this was the start of an explosive growth of interest among physicists from different areas trying to bring their skills together to think about the climate problem. So physics can help with understanding climate change, and I'm going to tell you some aspects of this. It can help with reducing carbon emissions from our energy sources, and possibly it can help with repairing the climate system. So we'll take each of these in turn. So understanding climate change. Oh, here's a picture of the Earth from space. Sunlight, visible light is impinging on it, providing heat, warming that surface. Some of that light is reflected off, about 30%, that's called the albedo. The rest warms the surface or in the ocean, and then is re-radiated as infrared radiation. This is a picture of my house in Providence, Rhode Island. We have solar panels on here on the house. We've completely disconnected from gas. So we're able to use that solar energy to heat the house through heat pumps, heat our hot water, and also we drove across the country, because I've been on sabbatical in California, of our electric car, and those solar panels produced more than enough energy to propel us all the way across the country and back. So it's eminently possible to have a zero-emission lifestyle. It's still rather expensive. I can afford to do this. We need to lower the costs. But I just want to hold that out as an example of what is possible. Now, the most important factors in the climate warming are water vapor and carbon dioxide. Water vapor is very efficient at absorbing infrared radiation, and so is carbon dioxide. Now, carbon dioxide is what we've been adding to the atmosphere. Water vapor responds to that because as the Earth warms, more water evaporates from the ocean. For every 1 degree Celsius of warming, about 7% more water vapor goes up into the atmosphere. So that's why we've been seeing this greater intensity of hurricanes and flooding events. Oxygen and nitrogen, the main constituents of the atmosphere, by contrast, are largely transparent to infrared radiation. So if we look at the Earth from space in an infrared wavelength, so one of the wavelengths that the water vapor interacts strongly with, we can't even see the surface of the Earth because it's the gas that we're seeing, the water vapor that's obscuring the surface. And in fact, this is what we're seeing is approximately 5 kilometers up in altitude. The water vapor begins to get thin enough that the infrared photons can escape out into space. And just knowing that fact is enough to understand the temperature of the Earth, which I'm not going to guide you through that calculation tonight, but this is the kind of the prime fact about our climate system. Now, I want to tell you about a remarkable woman named Eunice Newton Foote. Newton, her maiden name is because she was a distant relative of Isaac Newton. She lived in the middle of the 19th century, and only recently did climate scientists realize the important contribution she made to our field. She was a women's right supporter, and she participated in this women's right convention, women's suffrage in Seneca Falls. You can see her name right here. She was acknowledged by Susan B. Anthony. Here's a photo of her. So she wrote a paper, which is the very first time that we realized that carbon dioxide and water vapor interacted with infrared radiation. And this is the paper. I want to read you the sentence. He says, thirdly, the highest effect of the sun's rays I found to be in carbonic acid gas. That was the old-fashioned name for carbon dioxide. He also said the actions of the sun's rays were found to be greater in moist than in dry air. So she's recognizing the important role of water vapor. So this person is both a proponent of democracy, is advocating for women's rights, and science. And this is the very first appearance where we begin to understand how the addition of carbon dioxide into the atmosphere is changing our climate. Still understanding the ramifications of this discovery. This is a paper from just a year ago where finally the quantum mechanics of how a carbon dioxide molecule interacts with infrared radiation was worked out. So climate physics is still making discoveries at this very basic level of the ramifications of Eunice Foote's discovery. Now, right now, climate scientists are feeling pretty much under the gun, especially young climate scientists. American Physical Society is trying to establish an award to recognize young career climate scientists named after Eunice Newton-Foote. And if you're interested in learning more, you can just go to this website. Now, I want to show you a result of a climate model that's now almost 25 years old from the Intergovernmental Panel on Climate Change. So this is from year 1000 to, so back in the Middle Ages, to 2100 going into the future. And so we can see the climate as reconstructed from measurements and tree rings and various sources over this period of time. Now, going into the future, this is the kind of extrapolation in the Earth's temperature predicted. Now, this isn't the most recent model by any means. It's from, as I said, 25 years ago, but the results haven't changed. The results are the same. And the results are the same because the basic physics that Eunice Foote discovered holds. It's actually it doesn't even require a complicated computer model to understand this. And most of the uncertainty in the spread in temperature is not due to the uncertainties in the climate model itself, but rather in human behavior. How much carbon dioxide will we add to the atmosphere this century? So that's a theme that I want to also come back a little bit later. Now, the changing climate is much more than just the increasing temperature of the Earth. There could be changes in storm tracks, can be changes in the El Nino Southern Oscillation. There are many things to understand, and climate scientists are hard at work trying to do that. It's a healthy process of science with lots of disagreement. One area that I've been working on is waves of what we call topological origin. We noticed that there is a strong connection, mathematical connection, between electrons that travel around the edges of a device called a quantum Hall effect device, and waves that travel along the equator of the Earth's planet. And the connection has to do with the mathematics of topology, that is, the shape of things. So this is the Mobius strip. You wanted to, so if you move around from one side here, if you move around on one of the surfaces, you start off from the inside and you end up on the outside. And if you wanted to fix that, you'd have to snip that piece of paper and undo the twist and tape it back together. So that's an example of topology. So we found that there's a connection between that and something called the Kelvin wave, this pulse of warm water that controls the El Nino, which also has quite a bit of influence on weather in Colorado. I don't have time to explain that whole story, but if you're interested, an online magazine called Quanta Magazine has a very nice article about that, how quantum physicists explain the Earth's oscillating weather patterns. Let me turn now to reducing carbon emissions. So last year, on April 18th, California produced entirely renewable energy. This is the consumption of power in megawatts over the course of 24 hours. So this is noontime, this is midnight. And so this is the consumption here. And you can see that over this range of time, the production of carbon-free energy exceeded the consumption. And so this large orange area, that represents solar energy. So that's concentrated around the middle of the day. This other contribution that's rather steady is wind power. Then there's some other sources, such as geothermal and so on. But mainly, wind power and solar are the main renewable energy in California. There's also a little bit of nuclear from Diablo Canyon. So wind power complements solar power in time. We can see that the wind power is rather steady. And it also complements it in space because strongest winds are found off the coasts and in particularly at high latitudes. At high latitudes, there's relatively less sunlight. So there's this nice balance between sun power and wind power. California has a very ambitious plan to exploit that offshore wind energy by putting floating wind turbines off the coast of the state. The design of these wind turbines is still being worked out. Have to float because the continental shelf drops off so quickly that, unlike on the East Coast in Rhode Island, where we have wind turbines too, but they're anchored to the seafloor, here they have to float. And figuring out how to do that is an important engineering task. I wanted to emphasize the size of these things. So these wind turbines are going to be compared to the Washington Monument, something like this. The size of the floats are comparable to a baseball field. So these are enormous devices to maximize the wind energy that's intercepted. Here's a picture of one of the county supervisors for Humboldt County in California visiting New Bedford, Massachusetts, where she's seeing these huge turbines and these blades being erected offshore, sunken into the shore. So we've been trying to understand a little bit better how the energy can be optimized from wind power using combinations of ideas from statistical physics. So traditionally, one runs a supercomputer simulation of a wind turbine and tries to understand the turbulent wind that emanates from that wind turbine. So this is very costly. It requires large computers, large amounts of time on a computer, and this is just a single turbine. We'd like to understand a farm array of turbines, such as off the coast or on land too. We've been using an idea called direct statistical simulation, and it comes from the father of chaos, Ed Lorenz, who said that more than any other theoretical procedure, numerical integration, that's basically simulating the detailed equations, is also subject to the criticism that it yields little insight into the problem. The computed numbers are not only processed like data, but they look like data, and a study of them may be no more enlightening than a study of real meteorological observations. An alternative procedure which does not suffer this disadvantage consists of deriving a new system of equations whose knowns are the statistics themselves. Physicists are used to doing that. So if we have some gas in a cylinder, we turn this crank and we compress the gas, we know the pressure goes up. So that's the ideal gas law. It would be crazy to use a supercomputer to simulate the motion of all those molecules of the gas. Instead, we develop this theory of statistical mechanics, and we get at this very simple rule. So we've been trying to apply this now to arrays of wind turbines. So this is an actual picture of wind turbines which are interacting with moist air to make these this fog come downstream from them. And you can see that this turbine, for example, is shadowing the turbines behind it. So maybe engineers could figure out a way to deflect this shadowing effect by changing the orientation of the wind turbines to increase the energy efficiency. So a supercomputer view of something like this, looking down on the wind pattern, these little blue dots represent the different wind turbines, looks like this. And a student of mine has been running similar sorts of simulations on just a laptop. Our goal is to be able to hand a laptop to an engineer out in the field who's trying to figure out how to best orient and place wind turbines. So we're using this concept of statistical physics. In fact, that same quote was part of that initial Aspen proposal that I showed you at the start of the talk. This, just returning briefly to topology, at another Aspen program here, about 10 years ago, this fellow here, Jeff Parker, and I happened to bump into each other. He's a plasma physicist. We realized we could apply these ideas of topology to a plasma, and we've been doing an experiment at UCLA to look for these waves of topological origin in a plasma. Here's a picture of the machine. You can see these flashes are the flashes of plasma, and this type of device that's used to understand better plasmas for possible use in fusion energy. It has a particularly simple geometry that's particularly good for looking at waves. And we've been looking for these waves. And here's some of our preliminary results showing one of these waves traveling around the edge of the plasma, as we predict from this topological theory that was first developed here. Maybe this will be useful for developing fusion energy in the future. Now, we can't ignore the fact that these scientific discoveries or insights do not exist in a vacuum. An example of that is something called Jevons paradox. Does anyone know what Jevons paradox is? Good, yeah. So it's the idea that when we make, say, something more efficient, so for example, if we switch from incandescent lights to LED lights, and we save energy, what tends to happen is that people just start using LED lights more and more, and they leave them on at night. They don't bother to turn them off. So a very visible consequence of this is the light pollution that has grown dramatically in the past couple decades. When I first started coming to Aspen back in 1991, I think it was very easy to see the Milky Way, even from town. And now it's very hard. But this is true worldwide. So there's a kind of backlash that happens when we introduce more efficient devices, or when we produce energy more efficiently. Human behavior is very much caught up in this whole story. So let me now turn to the possibility of repairing the climate system. So we recently, in the American Physical Society, released a report examining the possibility of removing carbon dioxide from the atmosphere. So we're putting all this carbon dioxide up from burning coal, burning oil. Can we actually remove this? That's the question we asked. And we looked at a wide range of ideas and prototypes for trying to do this. And you can download our article here if you want. It's free. So what's the scale of the problem we're talking about? This schematic represents the flow of carbon between different reservoirs, for example, the soil and the ocean and the atmosphere. The ocean tends to absorb carbon dioxide about 2.9 billion tons per year. Soil also tends to absorb carbon dioxide, soil and plants, about 3.1 billion tons per year. But we're emitting about 9.6 billion tons per year from burning fossil fuels, overwhelming the capacity of the Earth to absorb this carbon dioxide. So 9.6 billion tons of carbon corresponds to 36 billion tons of carbon dioxide because of the weight of those two additional oxygen atoms. So I want you to remember that figure. We're right now emitting about 36 billion tons of carbon dioxide every year. Some of it's being absorbed, but most of it, about 50% of it, goes up into the atmosphere and stays up there. So can we possibly remove this carbon dioxide? So I want to give a brief survey of some ideas about how to do that. One is called direct air capture, building these giant machines that suck air through them and remove the carbon dioxide. Another idea is something called enhanced rock weathering, trying to accelerate the natural geological weathering of rock that tends to react with that carbon dioxide to try to remove it from the atmosphere. That's something that happens on geological timescales. Can we have it happen more quickly on human timescales? Ocean alkalinity enhancement is very similar, but it involves the ocean. And then there's ecosystem-based carbon dioxide removal, CDR. It involves, for example, allowing old-growth forests to continue to absorb carbon dioxide. So let's just look at the scale of the problem here. So we've classified these two different approaches to repairing the climate system in terms of what we call cyclic and once through. So what do I mean by cyclic? Cyclic means that there's some machine that has energy input to it that will then concentrate the atmospheric carbon dioxide into pure stream that can then be injected underground and hopefully stored, and hopefully it will stay underground. So that takes some energy. And it's like, the analogy I like is to use a sponge to, say, drain water from a boat that has a leak. You'd have to use that sponge multiple times to remove the water and squeeze it overboard. Each time you squeeze it, you have to do some work. You have to use some energy to remove that water. So how much energy would be required to remove 1 gigaton of carbon dioxide? That's only 3% of our emissions. So another modest goal, right? 3% is not going to make much of a dent, but let's just use that as our standard of comparison. Let's try to remove 1 gigaton of atmospheric carbon dioxide. It turns out that would take 14 gigawatt years to do that because of the energy required to concentrate that carbon dioxide, to reduce its entropy locally. So that's like having 14 nuclear reactors running for a year in order to remove that carbon dioxide. That's at the absolute minimum. But when we're never going to be able to achieve the perfect efficiency, a more likely efficiency might be 3 to 10 times that amount. And so that would be, say, 42 gigawatt years to 140 gigawatt years. This bar here represents the entire electrical energy output of the United States. So that's the kind of energy required just to remove those 3% of emissions. This is perhaps the most famous or well-known device that's in operation in Iceland, Climeworks, that's removing carbon dioxide. It looks pretty impressive, but it can only remove about 36 kilotons of carbon dioxide per year. That means that you would need to build 1 million of these in order to remove all human emissions. And this one is in a very favorable location. It has cheap geothermal energy from the hot heat under the Icelandic hotspot, and also the carbon dioxide injected underground interacts with the hot basalt and forms carbonate. So it's a very nice place to store carbon dioxide. So let me turn now to this idea of what we call once-through removal of carbon dioxide. And this takes its inspiration from nature. So this is a picture of a mountain in far northern California called Marble Mountain. It's made of limestone. And you can see that the snow here that's melting has the water coming off in these channels. And the reason it's in channels is that rain that comes through the atmosphere absorbs some carbon dioxide, makes carbonic acid. That's the carbonic acid gas that Eunice Foote mentioned. And it reacts with the limestone to etch it away, and the limestone neutralizes that acid. And so this is the natural process by which Earth can remove carbon dioxide over long periods of time. The problem is it's too slow. So this is just some pictures of there's a lot of caves in this mountain, and these kids are exploring one of these channels where the weakly acid rainwater has eaten away in the limestone. So what we need to do is grind up rock very finely to increase its surface area and to increase the rate at which it reacts with the atmosphere. And so there is some energy required, but not as much energy as with the direct air capture, because the rock naturally wants to react with the carbon dioxide. So we take this extracted raw material and then we spread it on farmland or oceans to try to absorb carbon dioxide. And now the main constraint is that we need a tremendous amount of material. If we want to remove a gigaton of carbon dioxide, we need about a gigaton of crushed rock at a minimum. A more realistic number might be 3 to 15 gigatons of crushed rock. The United States produces about 1.5 gigatons of crushed rock, mainly for roads and so on, every year. So it's not, impossible to imagine doing this, but again, it is a huge lift. So as I said, what is envisioned is mining certain types of minerals like basalt or olivine or even limestone, and then spreading it over the soil in this finely ground form. So this is a picture of the Ice Springs lava flow in Utah. So you can see these are crop circles here. So this gives you a sense of the scale. And so this is about the volume of salt that would need to react with the atmosphere to remove that gigaton of carbon dioxide. So that just gives you a sense of the scale. And this is a picture from the Aspen Mining Museum I took showing that this technology to pulverize rock is very old technology. Very old technology, so it's well developed, but it's not particularly efficient. And an interesting physics question is to understand why it's so inefficient, why most of the mechanical energy goes into heat instead of breaking up the rock, and whether it could be made more efficient. This is an operation in Canada that is mining and pulverizing a mineral called wollastonite here. And this wollastonite is then spread on the soil because farmers want to use it to improve their soil. So there's some good co-benefits to adding this particular rock to soil. It can improve the nutrient balance for plants. So that might be an incentive for farmers to participate in a huge program of enhanced rock weathering. We can also add these minerals to the ocean and try to enhance the capacity of the ocean to absorb carbon dioxide. That requires a better understanding of the ocean circulation, where water is sinking, where it is rising, where the ocean is releasing carbon dioxide, where it's already absorbing it. Finally, there are various ideas to use biology in different forms to absorb carbon dioxide. So I was living in the city of Arcata, far northern California, among the redwoods earlier this year, and they have a second growth forest. The original forest was cut down about 100 years ago. Now there's quite large second growth redwood trees, and they have estimated how much carbon dioxide is being absorbed by those trees, and you can go out and $37 buy a credit that corresponds to 1 ton of carbon dioxide. So if you're going to fly across the country, you're going to release about a ton of carbon dioxide. So maybe pay the city of Arcata $37 to preserve their second growth forest. Now, as with all of these schemes, there are downsides, and one of those is that forests, of course, are susceptible to fires. There was a big fire that burned through Big Basin, the Santa Cruz Mountains, and through the redwoods. Killed mainly Douglas fir and not redwoods, but that releases carbon dioxide. Also, we don't know what the land ownership will be in 100 years, but we want to lock this carbon away for a long period of time. So I want to return now to this dramatic rise in the temperature that was observed in 2023. Doesn't seem to be as large this year, but it continues to go up. One of the possible explanations for that sudden jump, one of the contributions to it, is the cleaning up of the emissions from large vessels traversing the ocean, bringing shipping containers. The oil in these ships used to be very dirty, but in around 2021, the nations of the world reached an agreement to clean up that oil, which is good because we don't like this pollution down at the Earth surface level. It affects human health. But these trails, you can see that the ships have left behind that created bright clouds, bright marine clouds that help to reflect light back out into space. So by cleaning up the emissions, it has the unwanted effect of darkening the Earth slightly and increasing the temperature. Now, that's not the only thing going on in that sudden spike in temperature in 2023, but this probably is one of the contributors. This kind of effect also is present in any effort to absorb carbon dioxide that involves very large land surfaces, such as the enhanced rock weathering that I described, or reforestation. So this is a picture of the redwood forest again in Northern California, and you can see how much darker these trees are than the surrounding grassland. So if we were to expand the redwood trees, that would darken the surface of the Earth, absorbing more radiation. And it's been estimated that this will cancel out about 30% of the benefit from the absorption of carbon dioxide from the growth of the trees. Now, returning to the enhanced rock weathering, though, you can see that this spreading of wollastonite actually lightens the soil. So here we might have the best of both worlds. We could reflect more light in the short term from the application of this whitish material to the soil, and over the long term, we address the root causes of climate change by absorbing carbon dioxide. This is a form of what's known as solar radiation management that has many other more controversial approaches, such as the injection of particles up into the stratosphere that would reflect light out into space. That's something that we think could be done at a relatively low cost, but there may be all sorts of unintended consequences. And we need to be very cautious about that and investigate this further before proceeding. I'll just point out that in the context of ocean alkalinity enhancement, here you see a recent satellite view off of New England. This is Cape Cod. And this white area is from coccoliths. These are little organisms that have bodies that are made of calcium carbonate. So they're reflecting light out into space, so that's good. But on the other hand, you'll remember that I said that we want to dissolve calcium carbonate. We don't want it to come out of solution and form limestone. Essentially, these are the things that form limestone in the first place. So these organisms are releasing carbon dioxide by the process of their formation in the surface waters. So if we put minerals into the ocean, what effect will it have on the growth of these organisms? So if you're interested more in these ideas, I have a preprint, a paper that I've written with a geochemist colleague of mine, and where you'll see some simple estimates that show that the change in reflection here easily dwarf the benefits from the absorbed carbon dioxide, at least over the short term. In this case, at least, they're both in the right direction. They're both having a cooling effect. So that brings me finally to the question of moral hazards. If we try to repair the climate system, if we deploy some of these technologies, especially the more controversial ones, such as the stratospheric aerosol injection, then we potentially provide cover for the continued pollution of the atmosphere. It's particularly acute in the case of this, the solar radiation management, because we're not addressing the root causes. We're reflecting more light out into space, but the carbon dioxide concentration is continuing to go up. So say we stop reflecting that light, then there will be a sudden pulse in heat that we would face on Earth. That's just touching the one of the basic concerns. There are many concerns, many moral hazards, because it's tempting to do this and then forget about the important job, which is reducing emissions. And I believe this is already beginning to happen. There are already companies that are hiding behind some of the carbon dioxide removal methods to continue polluting. So these are the kinds of concerns. Again, the human element is of crucial importance. So let me close by returning to the question that I asked. Can physics stop climate change? Well, I really should be more generous and say, can science and engineering stop climate change? Because there was a lot of chemistry, a lot of engineering, a lot of biology, and actually a lot of social science behind this. And so when I ask this question of myself, I would have to say, honestly, no. These technologies can be useful, but only people stop climate change, because it really depends on our behavior. It depends on our minds. That is the most powerful force that is at work here. these investigation of new ways to produce energy that don't release carbon dioxide, trying to understand the climate system better, trying to figure out ways to remove carbon dioxide from the atmosphere. These are all important things that we should be doing. It's not going to be enough, and we have to think about our own behavior. We have to think about the entire world acting together. Thank you.
Thank you for a very enlightening talk. So we're open for questions, and there's one lady in the second row.
In the foot, continually develop AI and quantum computing to these energy. And so, kind of like a
Right. Yeah, so the question is, are we shooting ourselves in the foot because we're developing new technologies like AI? Also, I'd add Bitcoin to that, which are consuming a lot of energy. Quantum computing, no, not yet, because it's such a small scale. It's insignificant. But definitely these other technologies you've heard about, different AI companies building their own power plants. They're using dirty fossil fuels largely. Yeah, this is a real problem. And this is, I would say, is a kind of manifestation of this Jevons paradox again. When we have this plentiful energy, we can just use it however we want, and that just encourages this kind of cycle. So I agree.
I'm in the front row.
So I appreciate the slideshow. At the beginning of the slideshow, you showed the amount color measurement location, which shows about 30 now. They're planning on that particular observatory now for reasons. Well, two things. One was, I love the idea of the trees being the most natural way to get carbon out of the atmosphere. If we planted more trees throughout the planet, that's be less invasive and probably less costly. The second one is observation that there's an eco that is based on COVID on the planet. At that period of time, everything's going up. It kind of dropped down real quick. And we never learned anything from that. Because if we were able to act quickly, see a huge change in the amount of carbon in the atmosphere just from a small period of time when people stopped doing certain things, it would seem to me that that was an example of what we need to do.
Right. Thank you. So, yeah, first it was pointed out that there was a plan to close that carbon observatory on Mauna Loa, Hawaii. Certain elements of the administration wanted to close it. There was a very strong pushback. Hopefully, it will continue on because it's has the oldest record from the 1950s that Charles Keeling started. But science in general is under great stress right now. Then the observation about that reforestation is somehow is a natural solution, which I agree, but it's not as simple as planting trees. You can't just plant trees anywhere, and even if you do plant trees, it takes a while before they start absorbing carbon dioxide. So if you disturb the soil, carbon can be lost that way, and it's a complicated system. It's a complicated ecosystem. The very best thing to do is to preserve existing old forests. Next best thing is to not cut down old second growth forests. Those are the most important things. Then as far as attempts to sort of reforest, that's much trickier. But in general, restoring ecosystems is probably something we should be doing anyway.
Try to avoid the physicists here in the second row.
What role does nuclear energy, serve in the ultimate solution?
Well, geothermal energy exists, and probably should be expanded because it's a nice 24/7 power source. So there are geothermal power plants in the United States, and we're learning ways to tap that energy better. That's having that steady power source is really good when you have things that are fluctuating like wind and solar. You can compensate for that by batteries, which are getting much better, but still having these steady sources of energy are very useful. Fusion right now doesn't exist as a energy source. There are a number of companies that are promising some results in the near future. There's one up in Cambridge, Massachusetts that's probably made the most progress. We'll know in a few years whether they have something viable. But even if it is viable, I am concerned that it may face the same economic problem as nuclear fission. Namely, it could be a very costly energy source. These are very complicated machines, and it's getting harder and harder to compete with solar and wind energy, which continues to decrease in price, and also with battery storage, which also continues to steadily improve over time. So both nuclear fission and fusion are facing just the economics may not be viable. We'll see.
We're getting more and more hands up. In the back there.
Right. So two things. You didn't mention methane source of climate change. I'd like your thoughts on that, number one. And number two, we're in the midst of a worldwide skin cancer epidemic, which is massive, and the stratospheric injection would help dramatically alleviate. And you mentioned that there's some hazard, but there's a positive side too. Skin cancer rates would go down dramatically with that reflective surface as an umbrella.
Okay. All right. So the question was, what's the role of methane? I didn't mention methane just for lack of time. So methane is a very important greenhouse gas, and we need to reduce emissions of methane. The American Physical Society, in fact, published a report just a couple years ago recommending some action for better monitoring methane leakage. So I fully agree that's important, and I just didn't mention in the interest of time. Now, regarding stratospheric aerosol injection, the amount of ultraviolet light or even visible light that would be reduced by that is not that much. We're not talking about darkening the skies. It might be a percent, say. On the other hand, there is the danger that it will damage the ozone layer. So actually, it could make it worse in terms of skin cancer. That's exactly the kind of worry that one has to think about. How the chemistry in the stratosphere of these particles reacting with other gases, how that will play out. And so that's where more research is necessary.
This gentleman
Regarding the additional the reflective sulfuric acid, I guess. And this is something every human, every animal, and their progeny gets to make such a decision.
Very good decision. Yeah, very, very good observation. Who gets to make the decision about whether to go ahead with this? And furthermore, it's something that a rogue billionaire could just decide to do, right? And so we need to watch out for that. We need to understand better what the consequences are. So some countries might want a slightly warmer climate. Other ones are going to suffer under a warmer climate. And how you decide these things, these are extremely difficult questions. Agree.
The young man in the so it seems like there might be a catch-22 between climate change and solar power, because I'm wondering if there are certain areas in the world that due to weather patterns that climate change it makes it unfeasible to install solar power because it's just not being able to let as much sunlight through as somewhere like a desert.
Right.
Yep.
The interaction, sorry, thank you. Question is, as the climate changes, weather patterns change, and that might affect these renewable energy sources, solar or maybe wind. So at my house, we've been getting more intense rainstorms, which darkens the sky. We get less solar power through those events. We need to think about that. I think it's maybe not a huge effect now, and hopefully the weather won't change that much that it will have a huge impact, but it might have some impact. And actually this stratospheric aerosol injection will reduce the amount of sunlight a little bit, as I mentioned, reducing solar power.
And I guess, gentleman behind the
With the historic changes in climate, back hundreds of thousands, millions of years, what were the physics of those climatic changes? And are any of those forces at play today?
So when we go back over when we go back over very long periods of time, the climate has changed over those long periods of time. And what's some of the physics behind that? First thing to realize is when we move from the human time scale, say a century, to the end of the last ice age, about 10,000 years ago, that's an increase in time scale by a factor of 100. So you can comprehend a century that's a few human generations. At 10,000 years is like 500 generations. And if we go back a million, it's just incomprehensible in terms of human experience. So when we look at very long time scales, or when we look at things that are very small, like atoms, or very large, like galaxies, the rules that we're comfortable with in everyday life begin to change. The things that are controlling them are things that we don't have much direct experience with. So in the case of the ice ages, which occurred, as I said, over the past several million years, those were primarily controlled by changes in Earth's orbit due to the interaction of Earth's orbit with other planets that changes the shape of the orbit. So those effects, those forces are still playing a role, but they are negligible over a human time scale. So when we go back, though, over these very large time scales, then geological processes that we don't have to worry about on human time scales play a role, astronomical processes, and so on. So there's a very rich and complicated story about the climate changing over the Earth's 4.6 billion years. Very interesting story, still being worked out because we lack a lot of information about the distant past. We do know some things. We have a pretty good understanding of the ice ages.
Okay, time's getting short, so I think we can take one more question.
So two things. First, some of the atmospheric injection research has found particles that might actually enhance it rather than destroy it. Also, in light of all the feedback effects that have been discovered, more CO2 or methane being released as a result of global warming, therefore, the runaway greenhouse effect is a serious concern, such that even if we cut off all our CO2 emissions, which we won't, that the forcing will that we will have a runaway heat effect. And in light of that, isn't some method of geoengineering going to be necessary to get us past that point?
Okay, the question is, because of positive feedback processes, where warming can release more carbon dioxide, which can then cause more heating, you could possibly get a runaway greenhouse effect. Something maybe like the planet Venus, where this has happened, which has an atmosphere that's nearly entirely carbon dioxide. It's 90 times thicker than Earth's atmosphere. The good news is that's not going to happen. So the positive feedbacks are not that strong. And furthermore, if we could suddenly stop carbon emissions, then the temperature will stabilize very quickly. That's a change in our story that has come with a deeper understanding over the past couple decades of climate science. We used to think, like I used to say, that because of the heat capacity of the ocean, it will take some time for the Earth's temperatures to stabilize, even if we could imagine, just say, no more carbon emissions right now. But it turns out that a more detailed look at that shows that the temperature will stabilize quite rapidly, and that these disastrous scenarios of a runaway greenhouse effect are highly unlikely. So fortunately, we don't live in that sort of world.
Okay, I think that's all the time we have right now, so let's thank Professor Marston.